Okay, hello everyone. Um, I'll just share my screen. Is it visible? Okay. Yeah, so first you look at this problem. Just take a minute to read it. I'll send the link. And think of how you can solve this. Okay, has everybody looked at the problem? Okay. So basically you're playing a game that consists of n levels. Each level has a monster. On levels 1, 2 to n minus 1, you can either kill or escape the monster. However, on level n, you must kill the final monster to win the game. Killing a monster takes SF time, where S is the monster's strength and F is your skill factor. Lower skill factor is better because you need to minimize the total time, right? So first you start with X, which is your initial skill factor, and there are n levels. So if you were to write a DP for this, you could say that if you are at index I, uh, at index I, so you can come from any index before it, right? From any level before it. So if we have dpi, and for example, we are coming from index j, from index j. So our cost will be the previous cost, which we incurred after coming to j, plus the skill factor, which will be from index j, into the monster strength. So Si, right? Oh, wait, yeah. Can you see the board? Uh, okay. So I hope everybody understands this. So we need to choose j such that this value is minimum. Hold on. Now, if we write the code for this, for example, um, I'll take the input and so. So this is the DP which we are making right now, the one I discussed right now. So initially the skill factor is X, right? So when you are at I, I should have used one based indexing here, but if you come directly from the initial skill factor, the cost would be dpi is equals to x into uh, si, right? This is the initial skill factor and this is the strength of the ith monster. And if you want to come from a previous monster, then for int j is equals to I minus 1, j greater than 0, j minus minus, dpi is equals to minimum of dpi and dpj plus fj into si. So this is what I discussed here. Then, since the problem says that you must kill the final monster to win the game, the answer would be dpn minus 1, which is the last level. So see how n minus 1. I'll just copy the input here. If I try this, the answer comes 4800, which is what was expected. But the problem now is that this is O of n square, right? So, so for I equals to hold on. For I equals to 0, it will perform 0 operations. Then I equals to 1, uh, it will go to j equals to 0. For I equals to 2, it will go to 2 indexes. So j equals to 0, 1. So this is 0 plus 1 plus 2 plus n minus 1, which is n minus 1 by 2. So O n square. So this is too slow, however. So this is where convex trick comes in, uh, which optimizes this dp to O of n. So the idea is that I'll just erase this once. Yeah. So if you look at this dp transition, uh, this looks a lot like the line equation y is equals to mx plus c. Right? Does everybody know what this is? This is the slope and yeah. Okay. So we can represent these as lines and uh, so when you're at index I, you have Si, so you want to find the line which gives the minimum Y, right? So for example, in this question, the f is decreasing, so the slope is decreasing. So if we draw a graph, right? So it would look something like this. So for example, for this, hold up. Okay, yeah. So in this region, this line would be the minimum. In this region, this line is the minimum. In this region, this is the minimum and this is the minimum. So we can just maintain these lines which give us the minimum values for these intervals of x, and we can use them to answer in ON. So I'll just show how you can implement this. So first we have a data structure for a line, which is the slope and constant, right? So we have two functions for this. One is int isect, which is what's the line? I do. So this gives the intersection point between two lines. So for example, if you have y1 is equals to m1x plus c1, and y2 is equals to m2x plus c2. So these are lines like these, for example, and you want to find this point, right? So we can see at this point that the y is the same. I mean, like x is the same, sorry. So hold on. Oh yes, the y and x both are the same, my bad. I'll just, yeah. So we can equate these two, right? So m1x plus c1 is equals to m2x plus c2, right? So m1 minus m2x is equals to c2 minus c1, and x is equals to c2 minus c1 by m1 minus m2. So all the intersection function does is find this x. So we have two lines. One is this line and one is the one we passed in the function. So we'll just do return uh, o dot c minus c divided by m minus o dot m. So everybody understands this? Oh, so because the initial skill factor is x, right? We are given in the question. Where is this? Initial skill factor, yeah. Oh, my bad. You can see this? I'll just try to open the chart somewhere else. Um, just give me a minute. Yeah, I'll tell that soon. Just give me a minute. We'll need this intersection function later. And one would be the, so for each line we'll have two functions. One will be the intersection and one will be the operator, the call operator. I mean, uh, I'll just write it. So what this function will do is give the value at x, the y value at x, return m into x plus c. So we'll use this later, and we'll implement the convex hull now. So as I said, the idea is to maintain the minimum lines. I'll use red for this. Um, yeah, okay. So we'll maintain these, the lines which give us the minimum value at a specific x. And we'll use a deck data structure for this. And this will have another two functions. One will be the add function, in which we'll add a line to the hull, uh, line L, for example, and one will be the query. So we want the minimum value at the specific x. So in the add function, uh, first we'll try to remove all the lines which are irrelevant. So this is where the intersection function comes in. For example, you have these lines, and you add this line. I'll just mark it as red. So these lines are already there, and the red line is the new one. So, okay, I'll draw it differently. Uh, so let's say, for example, that the red line is something like this. Okay, like this. So we can obviously see that the red line is much better than the line before it, right? The line above it, because it's always giving the minimum value there. So for this, we check these intersection points. If the line's intersection point is before this one, then obviously this line is not useful anymore because this gives a better answer. But for example, you have these, and the intersection point is here, like after this point, then it's not useful, right? It's not useful. I mean, this line is still useful, and this will be useful later. It's not useful here. So I'll just extend these. Then we'll be using this line here only, and here we'll use these. So if you were to implement this while hull.size greater than or equals to 2, so basically when we have two lines left, these two, and we want to check if this line is still relevant, and hull 0 dot intersection, uh, yeah, hull 1 greater than hull 0. Wait, I'll just, yeah, so this is the latest line. Wait, I meant to do this. Yeah, so basically this is hull 1 dot isect L, this one, and this is hull 1 dot isect hull 0. This is, wait, this is hull 0, and this is hull 1, and this is L. This is the new line we're adding. So we check the intersection point if it's before this one, then we can just remove that line. Uh, Hide option. So we are removing this line if it's not useful anymore. And then after we've removed all the useless lines, we can just insert it, insert the new line again. Push front, head. Okay, did everybody understand this? Yeah, this is the intersection function. Yes, it returns the x coordinate where these two lines intersect. Yes, it may not be an integer, but in this problem we only deal with integers, so we don't need to use a fraction or anything, or a double, for example. Yeah. So all this function does is remove the useless lines and insert the new line. All right. Yeah. So now the query function, when we need to actually find the value, the minimum value at x. So I'll just try to scroll. So actually, I forgot to talk about some constraints in this problem, that the x values, which is s. Uh, Let me show my board. Yeah, so here, this is x, right? X, m, and this is c. Yeah, decreasing slopes. Decreasing slopes and increasing x. So, hold up. Okay, yeah, x is increasing, so that makes our query function easier. Because when the x is increasing, you can remove some lines that are useless while querying. Because, hold up, let me explain better. So, for example, you have these lines, something like this, and you are querying here, right? This is the x. So, when you try to query, you know that this line will never be useful anymore, right? Because all our future queries will be here somewhere. Oh my God. Yeah. Hold up. Yeah, so you have a hull like this, and your query is here, x, right? You can see the whiteboard now? Okay. So here we know that all future queries will be somewhere here because x is increasing, right? So we can remove this line because it's not useful anymore. So when we're querying while hull dot size greater than equals to 2, of course, and hull dot back x is greater than hull, hull dot size minus 2 x, hull dot pop back equal hull dot back. Okay, so we are able to call this line like this because we implemented this, the call operator. It just returns mx plus c, right? So we're just checking if, I'll just label them here. So this is hull dot back, and this is hull dot size minus 2. Okay, so since we since when we add the line, we add it to the front of the hull. So the back will be the line which was added the earliest. Okay, so now we check the value which this line gives at x and the value which this line gives at x. And if this line gives a better value, then we can just remove this because you know it will never be useful in the future, right? So we remove it. Hold on. Alright. So did everyone understand this? So even in the query function, we remove uh, the lines which are useless and we get the minimum value. All right. So now if I were to implement this, for example, now initially, hold up, let me share my screen. Yeah. So initially we can think of this like when we haven't defeated a monster yet, we can think this as, we can say dpj equals 0, like dp0 equals to 0 and f0 equals to x. Like for the initial scale factor. Acha, which part do you want to repeat? No, we cannot use vector in this case because we need to insert both at the front and at the back. So we need it to be double-sided. Query. So here we are just removing any line which is not useful, so which gives a greater value, right? If it gives a greater value, if it's not the minimum, then it won't be useful in the future since x is increasing. And then we just look at the earliest line which has the least, uh, value. This is operator overloading. So for example, for a function, you call it like this, right? For example, this out function. So I have my own structure, let's say my struct, and I'm overloading this operator, the one with brackets, which is called the call operator, to use it like easier. So for example, bool operator return x% u equals 0. So if I have an instance of this, my select s, so I can call it like this, is even. I can kind of use it like a function, right? If I say 2, it will give 1, of course. Okay, cool. So initially we will insert x comma 0 here. Uh, Hold out and add x0. So for the initial scale factor, you won't be adding anything at the start, right? At the start, your score is 0 or whatever the cost. And your skill factor is x, the one that is given in the problem. Uh, right. So now for each monster, we saw here that SI is x, right? So we need the minimum value of DPI at x, which is SI. So I'll just create a DPI array for simplicity. So DPI is equals to hull dot query SI, right? So this will pick the optimal J and output the J from here. And then we can add the line for this DP value too. Hull dot add mm, M is F and C is DP. So FI and DPI. And if I take this now, okay, hold up. I have to take care of the lines which have the same M, right? Because this can be 0. So basically, if the slopes are same, they're parallel lines. So we can just give it some infinity value for the intersection point. Yeah, 4800, yeah. So here we query the optimal value at SI when x is equals to SI, and then we add the new line for this dp value, which is uh, this m is equals to fi and c is equals to dpi. So were you able to understand this? Okay. So if I try to submit this, okay. Yeah, I think uh, we have to handle this separately. Basically, when there's parallel lines. So for example, if L0 dot m is equals to L dot m, then we can set L dot c is equals to min L0 dot c and L dot c and L dot pop in. So what I'm doing here is handling the parallel lines. So for example, you have this. These are the old lines and this is the new line, right? Actually, is there? Okay, I should use this. Never mind. Yeah, so these two are parallel lines. The one which is already there, this is L0, this is L1, and this is L, which is the new line. So if these are parallel, this is y is equals to m1x plus c1 and y is equals to m2x plus c2, for example. So obviously, if this has a greater c, it will give a greater value, right? So it would not be useful. And since this has a lesser c, it's gonna give a lesser value. So there's no point in keeping this line then. So what this does is if the previously inserted value, if the previously inserted line has the same slope, then we keep the line which has the minimum c, right? So if I check this now, uh, right. So does anybody have any doubts? Please feel free to ask. Okay then. So we'll move on to the next case. In this case, the thing was that we had these constraints, right? That the slope is decreasing and the constant value is increasing. Sorry, the x is increasing, yeah. But what if the x is not increasing? Then we cannot do this. Uh, we cannot remove the useless lines in the query. So here I was talking about. Here we could remove this. Here we could remove this line because we knew that all future x will be somewhere here, right? But if this is not the case, yes, then we need to binary search. So just in the query, uh, int l equals to 0, r is equals to l dot size minus 2, and answer is equals to, for example, l dot size minus 1, for example, and l star So now we have these lines, let's say, and this is 0, this is 1, this is 2, and this is 3. So now we'll binary search on these lines, and whenever we're at an index, let's say 1, so we'll check the intersection point with 1 and 0. If it is more than x, the one we're querying for, then let's say x is somewhere here, right? So then we can, yeah, x is for example here. And if this intersection point is after x, then that means that the optimal value is somewhere in these lines, right? In these lines. So let's say this intersection point, if we're at index 3 and we check the intersection point with index 2 and it's before x, right? So 3 won't be giving the optimal value because if we extend this, the value is somewhere here, but the optimal is actually here. So we use that fact to binary search. So if li.isec, wait, hmm, oh my bad, I'll made. If it is greater than x, then answer is equals to mid, r is equals to mid minus 1. Okay, I'll just take this. Okay, hold up. Let me just figure this out once. Okay, wait. I was supposed to. Okay, I'll just check this once whether it's correct. Okay. What's wrong? Maybe this, right? Okay, yeah. So we're just checking the intersection point like I described. And for example, the condition holds that this intersection point is after x. Then then the index is at 1, the optimal value is at 1, or it is one of the lines that are after it. Right. So, uh, wait. Yeah. So if this intersection point is after x, then we set the answer to mid. So just, yeah, hold on. I have to pick this. Yeah. So mid is 1, and since the intersection point is after x, it's gonna be 1 or one of the lines after it, 2 or 3. Why is the line after the line if intersection point is after x? What do you mean? Oh, why are we setting L to mid? No, so if we're at 1, for example, and this is the point we're querying for, and the intersection point with 1 and 1 minus 1 equals to 0 is this. So that means that this 0 line is uh, valid only after this, and any line before it is also valid after this. Why are we setting to mid plus 1? Because if this is mid, then mid plus 1 is this 2 and 3, right? It would be one of these lines. Oh, my bad. X is not increasing, yeah. So we're blindly searching through all the lines. We're not removing any lines that might be unuseful before it. Okay, got it. Please let me know if you did not understand. I'll try to explain. And we use Q instead of deck. Not in this case because, hold up. Actually, yeah, here we can. Well, not Q, but vector. Q to you can't index, right? You can only access the first value. Yeah. If I use vector here, vector, pop back. I'll have to change the index order because we were inserting in the front earlier, but we'll have to do back if we use vector. Dot size -2. Oh, back. Um, that's Okay, we'll have to change this because we changed the order of the index. And oh yeah, what did I mess up? Huh. Why we changed the indexing? Because we were pushing to the front, right? For vector, we have to push at the back. Uh, oh yes. Yeah, so now if I submit this, yeah, right. So we can use vector here too, since we do not need to perform operations at both the ends. Yeah. So now we come to the third case, which is monster game 2. So this is the same problem, except there's no constraint on S and F, like the order. They're neither decreasing nor increasing. They can be arbitrary. Deck is not supposed to be faster than vector, is it? Barely. Yeah. Okay. So now if the lines are also in any order, uh, and the queries are also in any order, then we need to use a set to maintain these lines in the order we want, right? So for that we use there's multiple implementations. The one I'm gonna teach is line container. So actually we'll have to change this too. So now hold on. Line container. So this part will remain the same. We'll just change the implementation of the convex arbitrary. So now with the line, we'll also maintain the intersection point. So mutable and p. So this mutable just means that even if this line is a constant, we can still change the value of p. Now we'll have two functions for this, two comparators, bool operator greater than constant and constant. So we need two comparators, one with a line and one with an integer. So when we're comparing with a line, we want to compare the slope. So return m greater than o dot m. And when we're comparing with an integer, as in the x, we'll we'll compare the point, this p. So I'll explain this later when we actually use it. Uh, x, right? So now a line container will be inherited by multiset. So this line container is a subclass of multiset, multiset of lines. P is the intersection point with the next line in the set. So we'll have to maintain this. I'll show it later. Line and greater. So basically we'll maintain these lines with decreasing n. Uh, Basically it's a multiset but a custom implementation. So we'll add some custom operations to it. Yeah. See, this will become insert. Okay, add action. Yeah. We're basically extending a multiset to perform some additional operations. So first will be our intersection function, of course. Bool aspect iterator x iterator y. These x and y are lines only. So basically we're checking the intersection point when the line y is added. So if y is equals to n, I'll explain this later. Then return equals to in false. Yeah, so this basically means that if there's no line after x, then the intersection point is just infinity, right? Because there's no line to intersect with. If the slope is same, m is equal to x, m is equals to ym, right? If the slope is same, then the line with the lower c value will remain. So return xp equals to x is smaller than y c. It I'll just it's this xp is equals to if xc is less than yc, then it would be in, otherwise minus n. Inf means that it's always better than y, and minus inf means it's always worse than y. Else, then this is the same thing. Xp is equals to xm minus y, x c minus y c divided by y m minus x m, right? And we return whether, hold up, give me a minute. Mhm. Yeah, we return if xp is greater than or equals to yp. So basically, if x is more useful than y, uh, so now we have our add function, void add int m int c. So hold on. Yeah, we'll maintain three pointers here. The previous line. So first we'll insert this into the multiset, uh, MC, then the point is just infinity, for example. Then uh, current is equals to previous, and next is equals to, okay, I should do this first. Next. So initially, current and previous is the line we just inserted, and next is the line after it. It's a bit confusing, the statement, but that's how it's. Then we want to remove any lines that are useless after it. So which are useless and after them in the set. Right. Why? I see. So while current is, we calculate the intersection point between the current line and the next line, and because this function returns whether the current line is more useful than the next line. So if it is more useful than the next line, we just erase the next line and we get the pointer to the one after it. This arrays function will return to the element immediately following position, right? So with just this line, we are removing any line after it which is useless. Yeah, it's inserting into the multiset. Then if to begin. So if the current line is not the first line in the set and the line before it is more useful than the current line, then we remove the current line too, and we calculate the intersection point with the previous line and the next line. Then so while there's a line before the current line and uh, the line before it is more useful than the current line, then we again erase the current line, right? Yeah. So that's all it does. It's a bit confusing. So with this, we maintain three pointers, one to the previous line, one to the current line, and one to the next line. Then, and initially the current line is the one we just inserted. Then while the next line is useless, we just erase it because we won't be using it anymore, of course. Uh, then if the line that we just inserted is not useful, we erase it too, and we get an iterator to the next line, and we calculate the intersection value. And while the previous line is more useful, we keep on erasing the current line. So does this make sense? Okay, cool. Now the query function is uh, very simple. We just use lower bound and this is the value, y value, just mx plus c. This lower bound is the same thing as what we did in the previous implementation, uh, this binary search. So this thing and this thing is the same. I'm just using an inbuilt function to make it shorter. And let me just check if this works. 2600. Let me check the errors. 3600, yeah. Okay, cool. Please let me know if you have any problem with this.